My name is Presley Mays, and I did Experiment 5, Rates of Chemical Reactions. So our objectives were to learn about kinetics, to learn about the reaction rate, and to learn about rate laws. The hypothesis was that as the initial concentration increases, the rate would also increase. And the purpose was to observe the reaction time, and we wanted to calculate the rate and the rate constant, as well as kinetic order. So for our experiment, we used 6 test tubes, a burette stopwatch, a cuvette, and a CHE120. It was vital that the CHE120 be set to 565 nanometers and make sure that it was set to read percent transmittance. This shows the preparation of solutions, the volumes for each experiment. Experiment 1, we used oxalic acid, deionized water, and permanganate. It's actually potassium permanganate, but the potassium is a spectator ion, so we will just refer to it as permanganate. And you can see the different volumes here, 5, 6, 1 for experiment 1, 10, 1, and 1 for experiment 2, and then 5, 6.5, and 0.5 for experiment 3. It was also important to take note of the concentration of the stock solutions. In the beginning, the oxalic acid was 0.755 molarity, while the concentration of permanganate was 0.130 molarity, and the overall room temperature at the time was 23 degrees Celsius. So it was important for us to first take the oxalic acid and place it in a burette with the deionized water. After that, the professor came around and added the permanganate. As the professor added the permanganate, we started the stopwatch concurrently. And from there, we mixed the solution thoroughly in the burette before transferring it to a cuvette. The cuvette was then placed in the CHE120, and we let the reaction take place until the percent transmittance on the CHE120 was just past 30%. That was when we stopped the stopwatch. So these are just some of the formulas that we used. We calculated the average reaction time in seconds. We also used rate equals the initial concentration of permanganate divided by the average time. And we also found the rate constant from rate equals K times the initial concentration of permanganate to the X order times the oxalic acid initial concentration to the Y order. And we calculated the overall order from X plus Y. So for our results, we actually observed that the reaction changed, the solution changed from a purple color to a dark yellow-orange. The purple color was from the permanganate originally, and there was no bubbling or fizzing observed in our experiment. This is a chart, table actually, that displays the reaction times that we found, and we wanted to make sure that we had 2 reaction times for each experiment that differed by less than 10 seconds. So you can see here that our average reaction times for experiment 1 was 233, experiment 2, 125, and experiment 3, 268, all in seconds. So finally, next we needed to find the initial concentration. The first step that we needed to take was use the formula M1V1 equals M2V2, where M is the molarity and V is the volume. Plugging that in, you can see an example of permanganate here, where we used 0.130 molarity, which was the given concentration. And we multiply that by the 1.00 milliliters from experiment 1, set that equal to M2, which is what we're solving for, and multiply that by the overall total volume in the solution, which was 12 milliliters. And we find that to be 0.0108 molarity, for permanganate. We also would do the same process to find the concentration of oxalic acid, and then we can finally find the rate by using the formula initial concentration of permanganate divided by the average reaction time in seconds. And you can see down here for experiment 1, we took the 0.0108, which we just found molarity, and divided that by the 233 seconds, which was our average time from experiment 1, and we found it to be 0.000046 molarity per second. Now we can find the kinetic order using this formula, K times the concentration to the X order, concentration to the Y order. And for this specific example, I actually held X constant and solved for Y. So you can see here we have our rates on the left side, and then we move over and we find, we solve for the Y because the X's cancel and the K's cancel. And we specifically chose these experiments so that we could cancel those. And by taking the log of both sides and dividing, we found that y was equal to 0.895. Once you know y, you can just plug it right back into the equation to solve for x. And now that we have both x and y, we can solve for the overall order by using x plus y. So 1.20 was the value found for x. Add that to 0.895, which is what we just found for y. And we got 2.10 for the overall reaction order. And now we can find the rate constant using the formula mentioned before. We've just set the rate from experiment 2 equal to k, what we're solving for, times the 0.0108 initial concentration of permanganate, plugging in the x value we found, 1.2, multiplying that by the concentration of oxalic acid to the y power. Basically, you find that k is 0.027 m to the minus 1 s to the minus 1. And because it is a rate constant, that means that no matter what experiment you used to solve for k, you would get the same answer. So our hypothesis was supported that as the initial concentration increased, the rate would also increase. And some sources of possible error could be that the permanganate was mixed too long before it was transferred to the cuvette and placed in the CHE120, or even delay in pressing the stopwatch when the percent transmittance just passed 30. So we just basically conclude that the initial concentration increases, rate increases, and rate is therefore concentration dependent. Thank you.